Hello, everybody. We're here today to talk about scaling to millions of patients. Medplum has been growing quickly along many axes, and our approach is unique. We want to make sure that the authentication, bots, automation, API work together seamlessly and are rock solid. And so in order to do that, we have to do a lot of stuff. And we have the Matts, Matt Long and Matt Willer, here to tell you about it. These are really hardcore infrastructure engineers with specialties in the regulated industry. Matt Long from Box, Vanta, PlanGrid, Matt Willer also from Box and One Medical. These two are real experts on how to make these systems scale. So thank you both for walking us through it. Over to you, Matt.
Cool. Thank you, Reshma. Yeah, just to kick things off, let's take a step back and first appreciate why doing FHIR at scale is hard. That may not be immediately obvious. It all boils down to the fact that the FHIR spec is written more like a wish list than a spec in a lot of ways. It's very open to interpretation. Depending on how much of you've read of it, you'll see lots of shalls, should nots, and mays throughout the document, which just leaves a lot of wiggle room for the ways that various providers are going to implement the spec. And one of the things that comes out of that, in particular when thinking about search, which is what the core of a lot of what the FHIR spec is that it leads to infinite query shapes. When you're searching for resources, you can combine an arbitrary lists of filters, modifiers of those filters, chain references, including other resources types. And all of this leads to queries that are just difficult to predict and nearly impossible to optimize for every eventuality. This flexibility that FHIR offers really goes a long way to undermine the standard performance tactics that you might use when engineering and managing a large-scale software application. Just as a very representative example, we'll take the humble sort parameter, the way you want to order the resources that are returned to you from a search. In most large-scale systems, you'd be restricted to just sorting by a few different fields that are very well known and well optimized for, with like optimal indexes or whatever you might be doing. That is totally thrown out the window with FHIR. You can literally sort your results by any available search parameter, and any combination of search parameters, not just one. And so that just would make it impractical or just incredibly resource intensive to try to optimize for every eventuality because it would be infinite. So how does Medplum deal with this challenge? We're going to talk about our experience with scaling FHIR, like Reshma mentioned, and it all is going to revolve around the spec. We do deeply believe in the FHIR spec. We preach that everyone should be storing their data as FHIR resources because we truly believe this will lead to faster service provider interoperability. Those are the F and the I from the FHIR abbreviation, believe it or not. We embrace the spec at Medplum. Our database schema and the way we handle search parameters, attempt to make them fast, is all based on resources from the published R4 FHIR spec, things like search definitions and search parameters. We could even say that we love the spec in Medplum. We've scaled the supporting tens of millions of patients, and we have a very clear roadmap to being able to support deployments with hundreds of millions of patients. That doesn't say we haven't had our scaling challenges along the way, but each time we've met these challenges, we look at them in a principal way and figure out ways to solve the problems and make Medplum ever more performant and efficient growing scales.
The cornerstone of our scale strategy at Medplum is observability, because you can't optimize what you don't know about. So we keep a pretty close eye on how Medplum is running in production in our hosted environment all the time. So the first step that we use is we have extensive dashboards that we keep an eye on every day. Up on the left, you can see we have in-depth metrics reported directly from the Medplum service through our open telemetry data pipeline. Then on the bottom right, you can see we also have detailed metrics from lower down the stack directly from our database instances. So we can see how the entire service is running from top to bottom. We also have proactive alerts set up so that we can get notified when the system is behaving abnormally before an incident develops. Another feature that we've invested in is in-depth request tracing. This is an even deeper investment in the open telemetry standard. This gives us a forensic level of detail on exactly what happened during a request. You can see here, this is a screenshot from AWS X-Ray, where you can see a request timeline laid out. You can see exactly what was going on, what database calls were being made, and how the request was processed. This is super useful for us in troubleshooting. And then the other tool that we have in our tool belt is the slow query log. This is reported directly from our Postgres database whenever a query takes a little bit too long to be served. This terminology query took over half a second to run. And what we get here is a very detailed query plan from the database about exactly which operations it was doing to gather and serve that data. This is a real wealth of information for us as we try to optimize the system from the database up. And for anyone who's curious, this is the problem in that very slow query. You can see from this little snippet of the query plan that it was individually checking every one of 74,000 rows against this condition, and it threw them all away. So this was very inefficient. And this is something that we would be looking to optimize in the future.
Well, with that, we're going to look at some features and projects that we've shipped recently based on our findings from our observability platforms here at Medplum. First off, we're going to go right back into kind of putting those query plans in the spotlight here. We're going to talk about optimizing token searches. Just briefly, tokens are a very common element type within the FHIR spec. They appear all over the place, things like observation codes or the identifier field, which appears on pretty much every resource, I believe. They consist of a system and a value and can be queried in any combination of those, just by system, just by value, or both, among other ways. Previously, before we optimized or made some improvements to the way we handle these searches, we stored tokens in a pretty normalized way. We'd have a separate table containing all those systems and values, and that would be joined back to our main resource tables. In this case, we're looking at the observation table. It turns out that when you're having to do filters on both sides of those tables, that can lead to some pretty nasty query plans, where we're once again having to read a lot of rows from disk just to filter them and then throw out most of them. Having to do these types of filters will lead to inefficient index scans, reading those millions of rows from disks, and in this case, taking a whopping 19 seconds just to, at the end of it, return 0 rows. There were no matching observations here in this query that was looking for the most recent blood pressure reading of this specific patient. After we went to work on figuring out how to optimize this, we decided in this case, the best solution was to eliminate the join altogether. And instead of storing tokens in a more normalized table, we would just store them in a hashed representation within the main resource tokens. Here, the benefits are we get to eliminate that join altogether. This gives the query planner more room to use more highly selective indexes. In this case, we get to see it combine the effects of 2 indexes. And here, instead of reading millions of rows from disk to throw them all out, wound up having to read no rows from disk. And for a big speed improvement, just 64 milliseconds versus the previous 19 seconds. And just showing the moment where we enable this new search approach, we can see here a graph of the load on our database just drop pretty dramatically right when we turned it on, to effectively not going to 0, but going down to the more normal acceptable load versus the previous absolutely humongous spikes we were seeing as we're going through a period of rapid growth. From there, let's zoom out a bit and talk about GraphQL queries. GraphQL is a very convenient way to query and get back lots of data all in one request, but it turned out it could be a performance challenge on the back end, to say the least. This innocent-looking GraphQL query is actually a lot of FHIR searches in disguise. If you've heard about it, this is the classic N+1 query problem, but maybe on steroids even. So just a quick audience poll or trivia question is, how many FHIR searches does this GraphQL query consist of? A spoiler that the answer is over 1,100, 1,101 to be exact, looking at those counts that we're asking for and just the nested nature of this query. First, at the outermost layer, we're asking for a list of 100 patients sorted by their family name. And then for each of those 100 patients, we're looking for their 10 most recent encounters. And then for each of those 10 most recent encounters, for each of those 100 patients, we're asking for all the observations that remain in the encounter effectively. Add it all up, and that's how we get back at that 1,101 searches. And needless to say, doing 1,100 searches packaged up into one little request is a huge spike in load on the server. So what can we do to reduce the impact and kind of burstiness of load? We wound up using 2 approaches so far to tackle GraphQL in particular. One is introducing data loaders. Data loaders have become a pretty standard pattern for tackling the N+1 problem when it comes to GraphQL. And what data loaders let us do are batch process these similarly shaped GraphQL fields, or in this case, these FHIR searches. For each of those list of encounter searches or observation searches, we can, instead of sending those off to the database individually, we can scrunch them into fewer SQL queries, fire those off to the database, get back the same data we would have got if we had sent them off individually, and just reduce a lot of those round trips and the overhead of setting up the connections to the database. This leads to 2 different wins. It's faster response time since there is less overhead, and it lets the database just handle these queries with less load from having to deal with fewer connections and incoming requests. It turns out, though, that data loaders weren't enough for our production traffic levels. And we've also introduced read replicas of our database to field most GraphQL queries. In brief, what a read replica is, it is a synced copy of our primary database that is primarily or exclusively used to offload read traffic from the primary database. And with the trade-off being that the data that's present on those read replicas have a slight lag from the primary database, which for Medplum hovers right around 10 milliseconds. We see this as a reasonable trade-off, just given kind of the types of workloads where GraphQL queries are used, where that's an acceptable lag. And just kind of like a fun fact, like the reason why these read replicas were so critical is even with these optimizations around using data loaders, just the sum of GraphQL queries alone puts as much strain on the Medplum's database as the all other database traffic in aggregate.
And then another feature that we've spent some time optimizing and enhancing is our terminology services, specifically our value set expand operation. If you've ever had to look for an ICD-10, SNOMED, or LOINC code in Medplum, this is what you're using behind the scenes. Under the hood, we're ingesting 1 million different coded values from the UMLS dataset, as well as 10 million different metadata properties on those codes and relationships in between them. And so efficiently querying all of that data took us redesigning these database tables from the ground up. And we just recently shipped a new enhancement to this that is synonyms. So previously, if you were searching for hives, you would not have found it because the technical term for that in SNOMED is a wheal, WHEAL. But we've recently ingested another 500,000 rows into the database containing all these different synonyms that you can use to search for things. So this will show up now. And we plan to use that same framework to allow for searching for the exact code if you already know the specific LOINC or ICD-10 code that you need. Currently, that query that I showed a little bit earlier is pretty inefficient. But if we model those as synonyms, we can unlock a much more efficient query pattern that should improve performance here significantly. And then in addition to optimizing and shipping all of these different features, we put in a lot of work just managing the service and keeping it up and healthy. And so to talk a little bit more about that, I'll turn it back over to Matt.
First, we're going to take a step back and just kind of what is Medplum's approach to managing Medplum service? And it all we like to think about is like your plumbing, Medplum should just work for you. You shouldn't have to think about it much. Just a fun piece of lore is the word plum in Medplum actually stems from plumbing, not the stone fruit, but we just thought fruit would be a much nicer logo than a toilet for you. But yeah, we have a quite strong performance culture at Medplum where site reliability and availability always come first, not just in engineering conversations, but in kind of all aspects, talking about product roadmap and just everything we do. We want to make sure that those two things are just always top of mind, that we're never going to do anything that'll weaken them. Very closely after that is performance, all the things we've just talked about before this. We care deeply about performance and keeping the Medplum service fast for you. Some of the ways we achieve this is by preferring, when all else is equal, a simpler architecture and having fewer moving parts and tools. This lets us more easily understand the entire system and stack. This minimizes complexity and minimizes the types of failure modes that Medplum can run into. And ultimately, at the end of the day, issues are inevitable on the service, but when we understand this whole system, that makes it much easier and faster for us to diagnose and fix the issues that do arise. Along similar lines, we aspire to have no scheduled downtime ever. Think about the services you use every day, like S3 behind the scenes. S3 never has downtime. And that's something that Medplum aims for and tries to get closer to all the time. This is a big engineering effort and investment. Things like doing online schema migrations, continuously reindexing your data behind the scenes when we do release these performance improvements. And then when we do need to upgrade our infrastructure, doing so in a rolling fashion so there aren't any single points of failure and the service remains available at all times.
Another critical component for us in managing hosted Medplum is data segregation and isolation, making sure that our different tenants don't have access to each other's data and different users within a project don't necessarily all have access to everything in that project. At Medplum, we've developed access policies and built them on top of the FHIR spec. And these will give you a really rich vocabulary for describing which types of data a user can access and what kinds of interactions they can perform on data. These policies get enforced on every single data interaction that goes through the service. And so it's really important for us to make sure that this is performant and efficient. So if you look very closely, you can see that a lot of these criteria have the same shape as a FHIR search. And that's really helpful to us. Behind the scenes, we're translating these directly into SQL query filters that get evaluated at the same time as the other search filters. So there's no extra server checks that need to be performed to check permissions or anything like that, which results in both better performance as well as better security, since there's fewer places where we can make mistakes. And then another really vital thing that we needed to keep the service up is to place guardrails around the different system resources that people can consume when they're accessing Medplum. We have a pretty standard rate limit to make sure that you can't overwhelm the service with requests. But we also have to consider that not all requests are equal. One batch request might have hundreds of data rights, and comparing that to a request that's just reading a single patient by ID or something, those impact the server and the database very differently. So we recently introduced a new FHIR quota system to give us the ability to measure like the weighted average of these different operations. And we've allowed administrators to set these limits at multiple different levels. So if you're self-hosting, you can set the default server limits. And then even in our hosted environment, we can set different limits on the project and even per user levels as well.
And with that, we're going to look at some of our upcoming scale and performance features. The one I'm most excited about is database sharding. What database sharding is allowing you to horizontally scale a database beyond just vertically making it bigger in a more powerful single database instance, being able to span that out to multiple databases that are working alongside each other. This will ultimately allow Medplum to keep FHIR performant at any scale of data. What all of you are most excited about is this means you could feasibly use hosted Medplum, but still have a physically isolated and single tenant database that's housing only your data, as opposed to our current multi-tenant structure. And of course, this is a pretty big compliance and regulatory unlock, just being able to have that isolated data. There's two flavors of sharding that we're looking at. First up is what I'd say would be most applicable to multi-tenant deployments, and that would be sharding by projects. As I mentioned, right now, all projects in a Medplum deployment are housed in the same database. If we were instead sharding horizontally, we could put different projects on different databases. And then what's more specified or special for single tenant deployments would be sharding by compartment. Here you can imagine if you have a quite large project that's already on its own database, instead of storing all patients in that single database, we could further scale out and allow different patients and all their related records as defined by the patient compartments to be stored on different databases. This would come with a few trade-offs with the exact types of queries and the edge cases you'd be able to make, but by and large, a patient is still co-located with all their related resources, and so you are effectively getting to use 95, 98% of the FHIR specs still within a single patient context. Another one is data warehousing. Right now, we know a lot of you have built your own ETL pipelines to incorporate Medplum, your FHIR resource for Medplum with the rest of your data. And we want to further facilitate ways for transforming your FHIR resources into a more OLAP, online analytical processing format, into a more friendly way to do that. You probably preaching to the choir here that it can be quite difficult to run aggregations on the deeply nested and really referential data that is FHIR. So we want to help you be able to flatten and denormalize your resources to encourage or to facilitate modeling across different resource types. This would greatly simplify both longitudinal and temporal analyses. Questions like, what is the average blood glucose across my diabetic patients? What's the mean time between diagnosis and treatment? And how often are labs taken within 30 days of a procedure? Whatever the questions are that are important to your business. And of course, the other big benefits of warehousing is that you're able to further integrate and enrich your FHIR resources and Medplum data with data from other systems.
And one more feature that I'm really excited to work on is terminology validation, building on top of all of the performance and efficiency work that we put into our terminology services. We would like to use them now in the future to ensure that all these different FHIR fields that are supposed to have values drawn from specific sets actually do contain those values. For each of these fields, that's going to result in some value set expansion for every single one of them. So doing this for potentially many fields per resource at write time means that this needs to be really fast and efficient, but this is something that we should be able to ship on top of our existing infrastructure soon.
Cool. Thank you so much.